So what we can do is transfer. So obviously we can transfer Ether, that's great. We can transfer to some other address. I want to transfer an Ether. I don't want to transfer an Ether. But I could transfer, let's say, a Gavin coin to that address. Or half of that. And that's as simple as that. You choose which token you want to transfer, and you transfer it. There's nothing additional, no additional complications. So they're all as easy as each other. Now, we also have, in addition to your own accounts, which of course you can create and rename, tag your tokens in, and so forth.
So there's a sort of option to import accounts from that source.
We can import them from a Geth key store. We can import them from pre-sale wallet, from private keys, from the recovery phrase. Lots of ways of getting your accounts in there. We also have an address book. Now, address books are like, for your friends and whatnot, so that you can at least tag other addresses with names, and it's very easy to send to names that appear at drop down, auto completion, all that sort of thing. And we can see some of the people that we know now. Unfortunately, with no, can I get into that?
Let's try to get into it.
I'm doing my phone.
Good. Okay.
It's Bluetooth. I'll sit next to you.
Okay. We've got a few other little surprises in store as well. One of the things that I want to show is this notion of applications. So, hands up if you know what a DApp is. DApp. Okay, so, for those not in the know, a DApp, or decentralized application, is the idea of something basically similar to a web application. So, like Twitter or Facebook or whatever else. Except there's no server, right? So you get rid of the server, and rather than using a server, it uses the blockchain. Potentially a few other technologies as well, like on some means of like downloading data, or some means of sending messages. But the critical thing is that there's no centralized point in the system where it can be able to be broker or whatever else. Now, these are some very, very basic example dApps. Centralized applications. At the moment, they don't do all that much interesting. One example is the registry. So we have a registry of names, and we can see there's some names that have been registered here. Another one that's maybe a little more interesting is the token registry. So these are all the various tokens that are on the system. So I mentioned earlier there was a registry where you could just register your token, and it would suddenly be visible in everybody's wallet. Well, this is it. This is a front end. This is the way of using the DApp built around that registry. And you can see there's lots of tokens. If we have a look, there you go. There's the digits DAO token, and it's got a bunch of stuff. I don't want to get too deep into the token registry stuff, but we can do things like look up particular bits of records, and it will give us information back. In this case, it's we looked at the image record, and it was the image of the token. Now, that's kind of cool because we can do we can associate largely arbitrary data with tokens, and we can do it in an entirely decentralized way. So it's actually fetched this image from the blockchain, but rather using a little hack that we cooked up, where basically you can host the image online and then say, actually the URL for this particular hash can be, you can find the data that hashes to this value at this URL. Okay, so you can kind of hint, hey, you can look here to find the data that you're after. But because it's all cryptographically hashed, the hash is on the blockchain, then we can be absolutely sure that the data that we're downloading is actually the data that is being meant to be downloaded. So it's not just as simple as if, for example, if you are able to have control over that URL and you switched it for some other image, then it wouldn't work because it would hash that other image and it would come to a different value to the ones on the blockchain, so it would ignore it. And we have all of the various tokens here, and it's super, there's the golem token, we can look that up, and do an golem token, and it's super easy to add a new token, right? It's just as simple as register the token, and you can select an account and register it, and then you can just type in the address of the token. And you can write the TLA and the three-letter acronym. Okay, no, that's it. Okay, good. Everyone understand? Okay. Now there's a few others. One of the more interesting ones that comes with it is this token deployment. This allows us to actually very, very simply and easily, let's suppose we want to make a new token. Then we can actually just create one. So I can just go, I've got the original account. Make a new token, make a simple new token. Which I'll call a few of these things, I'm going to make 100 tokens. Right, see more than large and more than wise. Now I can just click deploy. So what's this going to do? Well, it's going to create a new token, right? So just mint a whole new currency, just like that bank, one token, right? That's kind of interesting, right? But first thing it has to do, of course, is it's got to spend a little bit of ether to put it on the blockchain, inevitably. And in order to spend that ether, it's going to have to get my permission. Because I don't want some random decentralized application spending my money without my permission. Now we've been very careful to ensure that random applications can't spend your money without your permission in parity. Right? Now this is where the funky background comes from. So I'm just gonna open another one. I'm gonna move that one as it is for now. So you see there's a you'll see there's a funky background. See all the circles? Yeah. There. Now this is a procedurally generated background. Okay. So there's only the key that generates this background is stored in the local storage associated with this URL, with this 127.0.0.1.81.80 URL. No other URL on this computer can access that key that generates this background. Which means if you memorize this background and anything other than something having this background asks you for your password, you know it's not parity. Yeah. And that's kind of one of the critical sort of junctures where your secrets, the things that are actually valuable to you, are looked after. They're passed only using this very particular mechanism. So if we go back to the signer, now this is within a DApp, right? So you're using the DApp, and the DApp wants to know your password. It wants to send a transaction out. How can it do that if you're not allowed to enter your password into the DApp? Well, of course, you enter your password into parity. And how do you know you're entering into parity? Well, you look out for your background. You can see the circles here. So you can see that that's the parity background. Parity has to be a password. What does that mean in reality? Well, it means that this particular bit of HTML, the bit that you're sticking your password in, comes from, is an iframe, for those who are into web, but it basically means it comes from parity, directly from parity. It's not part of the DApp, because the DApp could never have spoofed this background. Because if this background, the knowledge of what this background is only available to parity, and things that parity sort of authorizes.
So that background changes with different accounts, and you can change the background as well. So it's unique for each type of user side.
So if we're bored with red circles, let's suppose we want green hexagons instead. Now, as you see, the background here has changed to green hexagons. This is probably not automatically, but if I refresh the page, now the green hexagons right? And the only bit of the system that could have known that it changed from red circles to green hexagons is parity, or anything running with the elevated privileges of parity, right? Anything with access to this particular bit of the local store of the ground. So that's kind of important, and it's basically us taking great pains into architecting a system that will safeguard your password, because in the past, not everyone has been quite so careful, and there have been issues of people's passwords getting stolen and transactions being done in their name with their money that they didn't know about.
And going forward, we're also doing password backup and things like that. But then right now, we don't keep any of your passwords, so it's not stored on the server. So you still have to be careful with the password.
So I'm gonna confirm this transaction. I've never actually done this before, so fingers crossed. It might actually work. I'm told it works. So I'm going to confirm it, and we'll see what happens. Okay, so I confirm it. What's going on? Okay. We'll leave it there. Anyway, sorry, so let's leave that for a second. We'll go to the other tab. Now, what else have we got? We've got a really nice contract interface. So anyone who's doing contract development with Parity will be maybe familiar with having to write Solidity and copy and paste like snippets of JSON. Has anyone done this before? Has anyone tried to write a contract and had to write? Yeah. Okay. Well, this is for you guys. All right. So yes, what we can do is I have these contracts here. They're contracts. They're on the chain. They have APIs. We can send messages to them, call into them. Tell them to do things. So here's one contract, it's called operations. Now, we have, contracts tend to have kind of classes or object-oriented languages. They tend to have properties, right? Properties can change. They generally give you information about what's going on with that particular bit of the system, that object, right now. So for example, the token registration has a fee associated with it, right? So the fee is how much you have to pay in order to register a token. In this case, the fee is denoted in the units. Wei is 1/10 to the 18th of an ether. Okay, so very, very little bit of an ether. And in this case, the amount of Wei is what's that? Billion, trillion, quadrillion, 50 quadrillion, which is approximately half an ether. Okay, actually, it's exactly.
0.05.
Oh, it's 20. So it's got an owner. That's the person that the account actually owns the contract, and they basically get to do. They can reset the fee and they can change it to their own. And there's a number of tokens. How many tokens are actually in it? There are 30, right? 30 tokens have been registered. And what we can do is do stuff like we can get some information from, let's say, a 3-letter acronym. So we're going to put a 3-letter acronym token in. Here's one of those Gavin. So there's one exists. And we can query it, and it will come back with information about it. Right? The identity is 0 as the first token registered. The name is Gavin. The base millions, so a million subdivisions per actual point. And there's an owner address which is here. And another address which is there. 2 addresses. Oh, the owner and the actual token address. Now, this isn't specially made for this contract. This gets made for every contract. So this is kind of a handy little tool to use if you're mucking around with contracts and you need to keep inspecting various bits of it, or you need to execute functions on it. So we could execute something on this contract, and there are a few bits that we can execute. We can register a token using this register thing, and then we have to enter the address, TLA, name, so it's kind of like a slightly lower level version of that I showed you, except it works with every single contract. Right? All you need to do is tell the contract, tell the system what its API is, and it will show it. Okay, that's something else. Let's see if this sort of thing is. Well, I'm not going to do it right now. Okay. I think that's most of the stuff now. Sign up, I showed you, this is just an initial, this is basically the same view as the information that's down here, except it's awesome.
This is a compiler.
Yeah, I will require.
The settings like.
No. Okay. So that was the first thing, that's parity. Any questions about parity?
So we do have some questions that come in.
Okay.
So the first one by Jared Hope. What is the token registry address and contract API? So I think it's, if you download parity, you can actually see it.
Yeah. The address is this. Can you see that?
It's all right, I'll find it.
Okay. And the API is, I guess it's probably, yeah. But you can find the source code on the GitHub, of GitHub, in the contracts. Any questions?
So on the user account security side, I'm wondering one thing. So one security problem that I think is not really well handled in pretty much any client is that if, let's say I have one app, and inside of that one tab I have some status. So let's say, for example, I have 1,000 major points. Then I open up another tab. And that other tab decides, well, it's going to attempt to send a transaction, and the transaction just happens to be a transaction which makes a call to the maker point contract that sends all of their maker points to some random ground rush. So the question is, like, how can we help users basically make it harder for them to accidentally press confirm on that kind of transaction?
Yeah, so this is essentially distinguishing between dApps securely. Because once you can distinguish between dApps, then you can essentially say, well, this transaction came from this dApp and this transaction came from that dApp. And the user's got a much better idea that actually maybe they don't want to authenticate the transaction that's going to send all maybe tokens.
Right. So one of the challenges here, I think, is that there's sometimes legitimate reasons for different dApps to, I guess, use similar things. So, for example, I have maker point, and it would be totally legitimate for a maker point exchange to actually get related things.
Absolutely. So the question now is, well, okay, so you've got a malicious app that for whatever reason you're actually using. I mean, you have to use it in order for it to send this malicious transaction. So now the question is, right, can the user be expected to know that a transaction from a malicious app that they're using is malicious? And it's like, well, if they're using malicious DApp in the first place, then it might be that they.
So are you kind of arguing that there's JavaScript code or a gap should be part of the thing that's considered trusted?
So ultimately, if you've got a malicious DApp and the user's using it, then there are only really two ways. So one problem is that they may have a fully trusted DApp, like the Maker Exchange, and they are super happy for that. They actually trust it. For whatever reason, they decided that, they've seen the source code, they have it audited, they know there's nothing crazy going on. Any transaction coming from that DApp should be allowed to pass, or at least should have a nice green tick next to it. Now that's fairly easy to arrange, right? We can do like DApp identification or authentication in order to ensure that the signer itself says this DApp came from, this transaction came from this particular DApp, which you like, and then so that I feel is a problem that we can actually solve. Now, the idea that there's a malicious DApp that the user's using anyway that's sending transactions that look like they might be legit. Now, if it's in there to say this transaction came from this malicious or this dodgy DApp that you haven't marked as green and it hasn't got a tick next to it, it's got a yellow question mark next to it. Then now it's does the user say, well, I didn't do anything, reject, in which case problem solved, or do they say, yeah, it's probably fine, confirm, in which case we need a better way of explaining to the user what this transaction is. Now that's a separate sort of kind of point. I think obviously that's going to be solved with means of explaining to the user in a language that they can understand what it is that a particular transaction is doing. Now I see two particular ways of doing this. The first is that spec, where you have people who annotate contracts, annotate the API, the interface of the contract, with natural language, where in such a way that the placeholders are used so that you can actually create real sentences of what's going to happen if this transaction goes through. Like, how is this transaction going to alter the state? It's going to send 1,000 make points to this address that's not in your address. The other way of doing it, which is another possibility, is to have what I call state different. So basically, this is what the state was before the transaction. This is what I've done. I've executed the transaction locally. Pretend, right? I haven't actually put it on the system yet. And this is what happens. This is what the state is afterwards. And I take a difference between the two. So if anyone has done Git or whatever, version control will understand. There's when you make source code changes, you can get a diff, which just shows you the difference between what it was and what it is now. Now you can do that for state as well. So then you get the thing of, well, the user's not going to be interested in random numbers in random places in contracts changing, unless there's some way of converting, because there's some code that understands what goes where in a contract that can describe what these changes actually mean. So I see those two.
So you basically just run all the constant functions in every other tab and trying to see if the user state with respect to the other application changed.
So you don't have to run all of the constant functions in every other tab. You should only have to run the. You can check which ones have changed, which contracts have changed. So you don't have to run those.
Is that a feature that's coming?
It's a feature that's planned. Our resources are limited, but we've already done the state diff stuff, so that went in a few months ago. So it's basically down to anyone who wants to write React components to actually interpret this stuff, plus maybe some pattern matching in order to actually place useful language next. So actually, there's I've got the internet. I don't know if show you. Right, if I go to here, then should go transactions. If I were running the test net, then these transactions, which you can see here, would actually have interesting stuff next to them that would describe what was actually happening with the transaction. We've actually done the first two steps of this, of exactly this. So we'll actually say, if it recognizes the ABI, the interface of the contract, it will say, this transaction actually executed this particular method. It sent coins to and then stick an address in there. But if it's an address that you know, put the name in there with the address, and so on. If it did so on this day, blah, blah, blah. It will give you a relatively nice natural language description of what. Unfortunately, I'm not really in the test net, and the only transactions I've got are boring means they can't really give any information. Okay. Well, let's just check. So, so executing the function register on contracts, then contracting, transferring blah blah blah, passing the following parameters, doing something. So you get that, and you can get some distance with this into having transactions be comprehensible to the user, but it's not amazing, right? It's good for developers, kind of a first step for users, but the real sort of the real target is to really go for this natural language specification or natural language deduction from statements. Okay, any other questions?
Have you thought about much about sort of social proof that could be used to help guide users in deciding whether an DApp is trusted or not?
Thought a little. So, I think, this notion of reputation systems is ever in the background, right? It's ever present. It's just sort of murmuring away. We're going to have to do this at some point. But, there's a few people that have kind of tried to maybe get a grip on the problem, but I've not seen anything really groundbreaking yet. But yeah, I think it's going to happen probably over the next year or two. Someone's going to actually put out a reasonable sort of effort into this direction. Now, one of the things that we're working on, which actually tell you what, I'll just switch to the test net and show you. So one of the things that we're working on is So one of the things that we're working on, this is for a 1.5 release, is one of the things that we're going to be doing for 1.5 is an SMS verification tool. So the idea is that when you get an account, you can, as part of kind of a user on-ramping, you can just click verify my account, and it will send you a text message. And you can do a transaction based on the text message, then you do the information in the text message. And your account will be given a sort of a badge or a certificate that says, F-Core have sent you a text message to a phone number that no one else has sent a text message to so far, and you have received it. Yeah, that's what the certificate means. Which in some sense gives a very limited but nonetheless concrete value of uniqueness on the blockchain. Now, once you've got uniqueness, however limited it is, you can do all sorts of other stuff, right? All sorts of doorways open up because it's hard to get many of these, right? Which means that it's cost to the user to buy a new mobile phone SIM card and get another token, get another address associated with it. Which means you somehow now want to actually behave of high repute when you're using this address. Yeah, so used as the basis to the reputation system, it can now be, you can now start to think about building a reputation system that you can bootstrap. Obviously, once a reputation system is fully going, like for example Facebook, there's no big problem because people already have a Facebook account that they're really proud of, it's got a long history and all the rest of it. But it's really hard to do initially, because initially no one's got a Facebook account. And it usually takes, a very long time, years in Facebook's case, of organic growth, before you can get to the point of having a solid reputation system with millions of identities that actually care about their identity on the system. So piggybacking off things like mobile phone verification and maybe someday passport verification for a much stronger proof of individuality, and potentially decentralized uniqueness verification. So there are ideas of doing like meetups where people kind of come along with their passport and everyone else sort of says, yes, I recognize this passport, and they put in a hash of the numbers and basically it's impossible to be in many places in the world at once. And so as long as all these meetups happen at exactly the same time, more or less, then you can get a fairly strong guarantee of uniqueness for anyone who turns up to one of these things. So there are a bunch of ways of doing this, centralized and decentralized, but the critical thing is to make something that's important to the whole world, right? That cannot be spoofed or cannot trivially be multiplied out. Because once you do that, then you get problems with civil attacks. And as pretty much anyone working in a sort of decentralized space knows, civil attacks are always there and murmuring in the background, trying to trigger you. So if you can, get some solid protection against civil attacks, you can normally go quite a long way to get these kinds of systems working. So what was the original question?
Social proof on dApps. But yeah, reputation, identity.
Yeah,
definitely the way to
so
go.
I think, in principle, once you get a reputation system, which you could bootstrap with these kinds of SMS verification techniques, then yes, you can actually have civil attack proof-ish ways of having people is that. Anything interesting?
Do you mind going through like some of the security features of having parity, maybe offline signing, secret storage if you have?
Yeah. Okay, so the architecture of parity is kind of built from the ground up to have different processes handle different things. One of our processes handles secrets. Now, it's not fully developed yet, we've still got some distance to go here, but the architecture is built in order to eventually allow secrets to be actually held in protected areas of memory that even other processes belong to the same user can't actually do. Now, the secret, basically when you're a dApp, you're within untrusted code, right? So if you're in a dApp, this dApp comes from the internet. It might be that you actually wrote it yourself, in which case you probably trust it. But by and large, even if you trust yourself to write a dApp, you might still make mistakes, which means you might still accidentally be sending transactions to the wrong place, or too much money, or all the rest of it, right? So it's really important that there's an absolutely solid pipeline from untrusted code running dApps, which want to use your secrets, right? They want to send transactions on your behalf. They want your secrets. All the way down to the secret itself, which is basically an unencrypted 256-bit value. Right? This generally comes from a JSON file, right? A file stored on the hard disk, which has the encrypted value in it, and a password that you provide, which then ultimately gets turned into the key to the encryption. Okay? So the JSON file is pretty easy to access. Right, realistically, all it takes is someone to have like a virus on the machine that's able to scan the virus. So now we get to the point of like, right, well, okay, if you've got a keylogger, then you basically get rid of it. But let's assume that you haven't, it's not got that far. So now what we want to do is we want to somehow write a dApp that's going to capture your password, because the password is the thing that's actually guarding this. In parity, the way that we avoid that from happening is we tell the user, don't type the password into anything that you don't recognize. Now this includes that. In fact, we tell you, we go as far as to say, there's only one place that you can legally type the password, and that is in a box with a particular background. Box doesn't have a background, it's not parity, it's not trusted code. Now once the password gets, the way that we architect this box with a particular background is through, using local storage in the browser. So local storage in the browser basically means that the actual code, the actual HTML, JavaScript, has to be running on a particular URL. In particular, it has to be served by a particular port, 8180, which is our trusted port, right? We only serve particular trusted bits of code out onto this port. Yeah? So if the thing is coming from localhost 8180, we know for certain it's our code, right? Which means we trust we haven't really made a mistake. It's relatively simple stuff, so it's probably fine. By all means, really. Now, once it gets out once we get it back in on through 8180, we're now holding on to hot stuff. This is the password. We don't want to be holding on to this for long, so we immediately pass it into the sign-up process. Yeah. Now, the signing process is the only thing that has access to both the password and the JSON file, and it only ever uses them both for a kind of very small period of time at the point where it's actually signing the transaction. So literally, it sort of unencrypts the thing into memory, signs the transaction with this secret 256-bit value, and then instantly forgets that. So that's how we manage that process, and that happens in one very particular process. That ultimately we're hoping to protect it, or even maybe use some of this trusted computing hocus in order to ensure that even a CPU's hypervisor can't actually look down his name.
Do you have workflows for an AGAP setup?
Yeah, at the moment it's less than great, but 4.5 we plan to. Okay, so there are two things here. The first is what we can do right now. So at the moment, if you want to call a wallet or a digital cold wallet, the way that we manage this is you set the laptop, you stick something on like FP, one of the things that we distribute with parity, which is able to take a transaction and sign it, and then give you back the transaction with a key that's still loaded. Okay? So,
format of that transaction. Can you do contract transactions and still read them on the offline machine to understand what is?
The offline machine wouldn't have access to any of the blockchain, so that we, I mean, in principle you could do it, but you would have to preload it with all the information you ever need before you make it offline.
But could you at least understand what function calls you're doing with what data?
So the way that we get around that basically is to say, on your local machine, this the transaction would have a recognizable QR code, which is just a hash of the transaction, and it describes to you what the transaction does with all that information available. And then on your sign machine, which is offline, it shows you the QR code that it's going to sign. Just so it's, and then match the QR code up with the thing that we were told that what actually it means. If it matches, then you can be sure that it's on.
You use QR for the transmission as well, that you don't have to do anything else.
Exactly, yeah. So one of the things that bothers me when I see these offline cold wallets is that I've yet to find one that doesn't have a fully interactive digital connection with the machine, i.e. USB, Bluetooth, whatever. Now this bothers me because I can't read what's in the firmware there, which means it could be doing anything. The computer, there could be issues with the firmware that allow a virus to actually stick arbitrary code on there, as happened in one of the attacks with these centrifuges. The viruses can get everywhere, and I don't trust that they can't get onto one of these things, no matter how much the manufacturers tell me, oh well, the code's very simple. No, it's going to work. No, sorry. That's not good enough. It's still far worse than a paper wallet. So can we do any better? Yes. We can actually have a non-interactive means of communication, which is to say a QR code. So video camera on the device. So I'm thinking this is something I'd like to prototype and about it. But think mobile phone rip out any of the radio communication stuff, right? Maybe even rip out the USB. So it's just completely dead. The only thing we keep is the screen and the video camera. Yeah, and then you when you want to sign a transaction, you use all the video camera against your computer screen, your laptop screen, and it scans the QR code. If you unsigned transaction, then it puts that QR code on your device, tick across, click the tick, and what it does is it signs it internally, and then puts you the signed transaction as a QR code, which you then hold up to your laptop's video camera. They were never able to exchange information over a digital line. The only thing that happened was two pictures went back and forth, and you can see both of them, which means it's very, very hard to hide a virus or any information that impacts is more than maybe a few hundred bits. And that's the kind of guarantees that I want for a significant amount of cash onto these kinds of manufactured bits of hardware.
Last question that I mentioned at the beginning was like economic seeds or something as backup. Is that something you have? Like in Bitcoin, you have Bitcoin.
Yeah. So this is something I put in to particularly Ethereum back in 2014. But basically, a standard way of turning a phrase into a secret. This particular standard way always ensures that there's a 0 byte at the beginning, so you can design that. Actually, I found out that this identicon scheme actually generates better pictures if there's a 0 byte effect. That's another nice bonus. Yeah, so the yes, no, the mnemonics. Yeah, so the way that we don't actually allow brain wallets directly, so there's no way of just typing out a password and generating a phrase from it. It's kind of it's murky waters into security when we start doing that. But what we do is we generate, I think, an 11 or 12 word phrase from a word, I think a word list of 10,000. And this works out to be around 160 bits, which
Is that one seed for all accounts or per account?
That's per account. So we haven't done any hierarchical statistics stuff yet, although that's something that's kind of on the back burner. I think it will be, but it doesn't mean that you can't choose pretty bits. And that's kind of nice.
They could just get the link address.
Yeah, I guess. That's about it.
Thanks.
Is Whisper slated for being implemented in parity anytime soon?
It's not planned yet. It's kind of vaguely. It would be something that would be nice to plan. I haven't. It's something that needs a bit of research done on before like spending a lot of time on it. So I wrote the initial prototype 3 years ago, which worked reasonably well. But I mean, we're talking like a dozen people on it. I really don't know how it's going to scale at this point. I haven't taken any efforts to design any kind of specific scalability mechanism yet. Now, maybe other people will, and maybe actually it's fine and it'll work fine for Ethereum's particular needs for the next year or two. But at the moment, no, is the simple answer. That's not to say that we wouldn't welcome anyone from the community. It shouldn't take too long. I mean, the initial version that I did took about a week or two. Any other questions?
So Gavin, I know you released a white paper.
It wasn't a white paper.
A white paper which had polka dots on it.
Yes.
Okay. So like.
Okay. So this is a collection of thoughts placed in a fairly structured manner about where we could take these kinds of consensus protocols next. So it's always, there's always lots of directions that you can go in, with technology. I think it's important to try and spread out as much as possible. Different people going in different directions, because you never know which one's actually going to carry on for you. So, in some sense, this is the direction I think is going. So, Polkadot describes, describes a technical proposal which would give us a what I call a heterogeneous extensible multi-chain. Okay, so these are kind of three new words. So multi-chain can be taken to mean many blockchains. Okay? So there are many blockchains in the moment, okay? But the thing is that they're entirely isolated. So the only way that you can get from one blockchain to another blockchain is through an exchange, basically. And exchanges only really deal with very particular assets tokens. They don't deal, for example, with arbitrary messages of the ilk that you can send and receive in Ethereum. Now, so that's kind of multi-chain bit. So then the other two, extensible and heterogeneous. So heterogeneous basically means that these chains don't have to be the same. They don't have to be the same type. Okay? So there are lots of different blockchains. Many of them are very similar. For example, all of the altcoins, basically up until Ethereum, were just forks from the Bitcoin code base with a few tweaks to the past. Okay? Now these are all basically the same type of chain, they're just reparameterized. But Ethereum came along with a different chain. Like it had contracts, it used a very particular state rather than just sort of who is spent or is not spent. And you could sort of send messages, so you could attach quite arbitrary data into how these different accounts interact. Now this is kind of, this was a different thing, right? Presume you can see that. Bitcoin is different to Ethereum, right? They're not just two different tokens, they're actually different beasts. Okay, cool. So what I wanted to do with Polkadot was to allow this to continue, to have different beasts, but have them inhabit the same roof, right? So they could sort of talk to each other without having to actually step on each other's toes. So for example, if you put, with Ethereum, Ethereum is general purpose, but there's still an issue that it's based on a particular set of parameters, right? So for example, with Ethereum, it's very difficult to get the sort of pseudonymity that Bitcoin has. It's much better designed for the kind of, I have an account and I keep that account. Yeah, so if I do an SMS verification on my account, I don't want that SMS to be, that verification notion to be transferred in the same way I wouldn't want a certificate of my degree to be able to be transferred to somebody else. Yeah, this is kind of by mixing up the notion of pseudonymous and not actually pseudonymous and properly identifiable. Ethereum kind of is in this kind of grey area. So what I'm kind of getting at is that there's, even though Ethereum is general purpose, there's still an awful lot of interesting experimentation to be done on blockchain architectures. And one thing that I was interested in addressing is, can we allow this experimentation to be done without giving up sort of interoperability or backwards compatibility? So can we keep the same chains going forward whilst developing out new, different, interesting kinds of chains, and yet still allow them to talk to each other in a trust-free manner? So we have to use exchanges and the necessary filtering, lowest common denominator, and necessary middleman fees that we're paying. So that's kind of the extent. So that's kind of what Polkadot aims to do. And the proposal basically works like this. You have a bunch of, so Polkadot at the root is a proof of stake blockchain. Okay? Now, all blockchains, proof of stake, proof of work, whatever, so far, at least to my knowledge, that have been implemented, have tied up the notion of canonicalization, which is to say, the ability to disallow double spends. Okay? The ability to come together in consensus on one particular history. Yeah? So we are here today. These transactions were executed in this order, all the way down to when it started, the Genesis block. Okay? Now, this is what prevents double spending. Because I can say, well, this transaction happened before this transaction, that made it invalid because it shouldn't be included. In the same way that if I've got $100 in my bank account and I write two $100 checks, whichever one gets cashed first is valid, and whichever one gets cashed second is invalid and shouldn't be cashed at all. Yeah? And the banks work very hard to ensure that this actually happens. As does Bitcoin. This is the great thing about Bitcoin. It prevented double spending by ensuring that there was one canonical history. So it's canonicalization, right? This is the thing where, you know, different transactions may individually be valid, but when one enters the blockchain, may mutually exclude the blockchain, right? So, you know, canonicalization. Now, the other thing is validity, right? Validity. So validity is this inherent notion of, is this transaction valid? Is it properly signed? Is it doing something, you know, is it saying something sensible? Is the, when I execute it and I'm told that this actually happens, does it actually happen? Is that a valid execution of this transaction? Yeah. So if I say, well, I executed this transaction and yeah, it turns out it gave me $1 million from nothing, that might be questionable. Maybe that's not what the transaction did. And so that would be an invalid reading of the transaction. Okay? So we have these two things. One is inherent validity and the other is canonicalization, or in some sense relative validity. Yeah? Now, so far, blockchains have tended to bring the two together. So the other thing I can tell you is that canonicalization actually scales quite well. Right? So lots and lots and lots of people can actually come together and agree on a bunch of history fairly quickly, and that history, because of it, we can use hashes to basically take an awful lot of data and turn it into a small amount of data. We can actually we can scale that to the point that we can canonicalize an awful lot of data at once. So canonicalization scales pretty well using protocol. But the problem is that validity and validification, that doesn't scale so well, right? So validation really does need to be parallelized. Where we split up and we say, you guys, you validate this bit, and you guys validate that bit, and you guys validate the other bit, right? Now that can be parallelized, but we're not parallelizing things at the moment. Why not? Well, because we're tying it with canonicalization, which doesn't parallelize well. Because we want to come down to just a single history, not three different histories. Yeah? So we have these two things. One is super serializable, and the other is super parallelizable. And so far, blockchain technologies have married them together, and that means that we get neither. Yeah, we can't serialize. We can't go in one direction and serialize both of them. We can't go in the other direction and parallelize both of them, because one of them only really parallelizes well, and the other one only really serializes well. Okay. Well, what Polkadot tries to do is split them up, and it says, right, we're going to do two different tasks. Yeah, we're going to do one task that's just about parallelize, it's just about validation. We're going to split up the problem and get lots and lots of different subgroups validating all at the same time. And then, separately, secondly, another task, which is canonicalization. And this is where we say, right, these guys have all decided that what they've done individually is valid, and we trust them because they're staked on what it's doing, just part of proof of stake. Well, now we're going to canonical it. Right. That's basically what Polkadot does. Now, Polkadot does that, and it's a bit different to some of the other things that are out there, in that the different things that are being validated don't have to be the same basic class. So we're not talking about shards, yeah? We're talking about like individual blockchains, more or less. They're actually slightly spayed blockchains in that they can't manage their own consensus because actually they rely on the main route, the relay, to do the consensus stuff. But other than that, they're perfectly free to do whatever they want. So their state transition function can be entirely arbitrary, because this is just a general function for validating what has changed, what these transactions mean, and how they're determined. So the way it kind of works, to grossly simplify, and sorry, I didn't have time to do slides, which would have probably made this an awful lot easier, but I will nonetheless do my best to explain it to you. The way it works is that we have 4 different roles. First role is validators. So validators are these guys, they're bonded, right? Which means if it can be demonstrated that they acted maliciously, they misbehaved, they can be punished. Yeah? Okay. And validators are nodes. They sit around and they validate stuff. Right? What do they validate? Well, every block they get chosen to validate a particular parachain, right? A particular one of these. So the parachains is kind of like parallel chains, the chains that work in parallel. Yeah, and then also kind of para means similar to something but not quite it, and that's also kind of ties in very nicely. So they validate these parachains. They get chosen using a cryptographic, unpredictable deterministic yet unpredictable means to validate a particular parachain, and this changes every block. Yeah. So every block they're like, oh, I'm on parachain 2, and then the next block, oh, I'm on parachain 8. While the bloke that's on parachain 8 before is now maybe on parachain 3. So yeah. So they're always moving around validating different chains. Okay. Finally, after they've each validated their own chain, or the chain that they were assigned to, they then come together and canonicalize. Yeah? So they basically say, this chain had this block in it, or this parachain had this block in it, this parachain had that block in it, blah, 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 all the way, and they say, this is what happened. This particular block, this particular super block. Right. Next rule, nominators. Nominators can nominate a validator. What this basically does is it increases the bond of that particular validator. Now, the way that nominators work, actually, there's a market mechanism going on. They can nominate, it works through approval voting, right? You all know what approval voting is? Approval voting basically means I don't mind who gets in or who takes my money as long as it's one of these guys. So I approve of, let's say, 5 of these 10 potential candidates. I don't care, I don't care which one of the 5 I vote for. It could be maybe a little bit of each of the 5, right? But whatever it is, it can't be these other 5. Not interested in those other 5. And this, basically, we have a constraint optimizer that runs every block and makes sure that these nominators get their nominations for which validators their bonds will go to is optimal for the system, for the security of the system, which is to say that the bonds are basically, each validator is more or less bonded to the same amount, and as much as possible. Because the more that they're bonded, the more that they can be punished should they fail to uphold the rules of the system. Okay, so nominators basically allow other participants to place their staking tokens under a one or more of these validators. And they entrust their tokens to the validators in order that the validators then, let's hope, act properly, and they will get some rewards for it. So validators are rewarded, and nominators for that matter, through the inflation of the token price. Okay? So new tokens are minted in order to pay these guys for maintaining this. In much the same way that Bitcoin and Ethereum tokens in order to pay for security. Now, in principle, if everyone puts becomes a validator or a nominator, then actually there's no inflation because their tokens are going up in proportion to all of the other tokens, and so they actually have retained on the same fractional value within the system. Okay, so that's validators and that's nominators. So there are 2 more interesting little things, and actually, in reality, these guys will probably be the same in the end. they're probably just other nodes, nodes that are chaining. Now these guys choose a parachain to work on. Yeah, so it's another sort of divide and conquer part of the system. So rather than there being, so validators are divided, but they're done every block, and in principle they cannot choose where they go, right? That's chosen automatically for them. So their loyalty is to the system as a whole, right? Whereas these other two groups, their sort of loyalty, the place that they actually hang out on, are individual chains. They choose one and they do a full sync, right? So they synchronize it fully, so they have all of the information available. Unlike validators, they cannot have all the information available because that would not scale. They were made to have all the information available for all of the chains, and when you added a new chain, it suddenly increased the vast amount of work that each validator had to do, and that's the thing. So we split the work between these two groups, collators and fishermen. Now, fishermen I'll come to later. Collators basically do the job that miners do today, right? So most of the miners' work is in collecting transactions that go floating around the system, executing them, and generating a new block, right? That a little bit of work is done to actually prove that, you know, this block should be canonicalized. This is the so-called proof of work. But basically, the most work is done is in collating these transactions into blocks. Okay, and that's precisely what these guys do. Their job is just to, for a particular parachain, go around, collect transactions, bundle them into a block, and attach a proof, right? But rather than proving that work was done or proving that state was given, we do another proof. We prove that they're valid. So we have a proof of validity, right? So the block comes with a proof of validity, which is to say it's a Merkle proof, or at least for Bitcoin and Ethereum blockchains, it would be a Merkle proof. For other chains, it may take a different thing. We don't. This is the beauty of the system. Could be it's unconstrained as to how it actually works. But it would be a proof that this block was executed correctly, and that the final state was indeed the state that's faithfully that you would faithfully get after executing these transactions. Yeah. So, and it's done in such a way that a validator, even though they know nothing about the parachain, right? The only thing that they know about is the relay chain, the main one sitting in the middle. It will be done in such a way that they can validate everything about that parachain block just from that knowledge. Yeah. So basically, think like client proof, but for an entire block. Okay. So that's what these guys do. That's what the collators do. Now, for their trouble, they can collect transaction fees. Yeah. And depending on, I don't know, maybe they also get paid a cut of the rewards that the validators get. That's sort of, we'll see, economic modeling. But in principle, they get the transaction fee. So that's probably going to be enough to pay people to get service to do this. Okay. Now, the final thing is fishermen. Fishermen are basically the guardians of the system. Now they watch out for validators that are not behaving properly. So if a validator validates a invalid block, says, yes, this parachain block, yeah, that was valid, no problem there, and then it turns out to be invalid, which you can instantly check because it has the proof of validity with it. All you need to know is the main relay chain information to prove that. Now, if a fisherman sees one of these and decides, sees that it's invalid, what it does is it reports that to as many validators as it can find, basically. And as soon as that becomes widely known that it's an invalid block, then the validators can get together and say, "Oh, this validator is behaving badly." Kick them out and take their block. So that's the basic explanation for how this stuff works. Now, there's a whole load of go on.
For the last role, how do you detect valid blocks that are on that are orphaned off?
How do you detect valid blocks?
An orphaned block is still valid, right?
By orphaned.
Well, you have two blocks at the same time, like Bitcoin or Ethereum, and one doesn't make it into the main chain.
Okay, so there are two levels of blocks. So there's the relay chain, which is kind of the big one, the root.
Also, you don't even prove the blocks, you prove the blocks that you create on the transactions. So that's a different block.
So the collators prove blocks on the parachains. So we've got a bunch of parachains and one relay chain in the middle. And the collators make a proof of validity for these blocks. Now there could be many of those at the same time, yeah? So let's say we're on block 42. So I don't know, 5 different collators for parachain A, say, you know, I've got A42, and then someone else says, oh, I've got A42, I've got another A42, and so on. And they all push it to the validators. You are maybe 5 or 10 of them are chosen to do this, to validate this particular parachain A for block 42. Okay? So they have to choose one of them, yeah, because that's their canonicalization. So basically what they do is this, they have a vote on validity, and at the same time they have a vote on canonicalization, and eventually they come to back in one of them, which is which they all decide is valid, and you know, in some probably, well, there are certain tie-breaking subtleties, but basically one of the valid ones eventually gets a bunch of votes to demonstrate it's the canonical valid. Now the other valid ones that are non-canonical, so kind of orphaned blocks in this sense, just fall by the wayside because they never got that number of signatures that are required to canonicalize the block. So these signatures eventually make their way onto the relay chain, so that anyone who's just following the relay chain can say, right, this block is canonicalized, and there are probably others, but we don't need to know about them because they never made it past the signature process.
Not sure if I 100% understand it, but would it be able to handle reorganizations of another chain?
So no. So reorganizations basically happen when the canonicalization mechanism of a blockchain fails. Yeah. So proof of work, you know, we're going along nicely, and then we go, and then it turns out, oh no, there's another fork. If we go 2 blocks back, then there's 2 blocks that are different, and then maybe another 3rd or a 4th block will come along, and we have to reorganize. So basically, it means we have to revert anything that happened in the 2 blocks that we thought were the last 2, and then potentially re-execute other transactions that are mutually exclusive in these other blocks going on. Now, that cannot happen within this design, because the canonicalization process happens on both the relay chain and all of the parachains all at once. So the only canonicalization that is happening is for the relay chain. The relay chain just points to blocks in the parachains, and only one block per block.
Two quick questions. How does the transaction know in which parachain it goes? Like, how do the transactions get pulled in one of the parachains?
Okay. Well, so the basic reading is they float around the network, and collators just listen out for them. The slightly more complex reading, which the paper sort of goes in a little bit detail to, is the network protocol would actually have means of subdividing the network into to allow different parachains to share sort of overlay subnetworks within the main peer network overlay. So basically, as a peer, I would tend to connect to particular machines depending on my role. And I will be able to discover which machines are most likely to be useful to me. I.e., suppose I'm on parachain A, I will be able to discover other parachain A machines through this peer-to-peer protocol. Now, I think this is already being worked on for the underlying peer-to-peer protocol of Ethereum, but I think it's a pretty important sort of mechanism for general peer-to-peer protocols.
The second question is, how do you do the canonicalization between the parachains and the relay chain? How do you decide the order of the blocks?
So the subtleties regarding deciding the order basically come down to a notion of magic ticket. So
this was magic.
So a little bit like with proof of work. Now the idea is that every block for every parachain there is a magic ticket, right? It's just a random number. It's deterministically generated, yeah, but unpredictable. Now this magic ticket denotes when combined with a distance metric, for example, an extra distance metric, would give you a score according to, and the thing that you would place on the other side of the score would be the address of the collator who collated that block, right? So different collators get basically randomly chosen scores every different block, every single block. Yeah? So then you say, oh, well, you know, a collator could just have millions of addresses and sign millions of blocks with, you know, all these different addresses, and eventually, sure, but it's going to cost them bandwidth because these blocks are not cheap, right? They contain maybe 2, 3, 800K, maybe even a megabyte for the proof of validity. So it's not simply a case of sending a million blocks. You would need a million times more bandwidth is all the collators, unlike that. But the other thing is that validators have a strong incentive to choose collators that have already had their blocks being included recently in the chain. This is because collators can in principle brief validators by giving them blocks that have a massive long proof of validity that takes ages to get through when it turns out to be valid. Yeah. So they're going to have to listen to some of these unknowns because, you know, it's a balance between, well, I want to be the validator that actually turns up with the winning ticket, yeah? Because the idea is that if you turn up with the winning ticket, you get a bit more reward. So they want to be the validator that turns up with the winning ticket, but at the same time, they're not going to get grooved, yeah? So they're going to basically, you know, there'll be some interesting game theoretic mechanism for choosing maybe n collators blocks to validate that, you know, you've never seen them before, but they're really close to the winning ticket, and then some other percentage of collators blocks that you know are definitely good guys because they've already had their blocks in the last 1,000 history, but you're, you know, they're not that close to the winning ticket.
I suspect that Gavin is understanding the history, but part of the idea of a multi-chain is that there's going to be a system considered complexes. We might have a consortium chain that has very higher scalability than the network, for example. But the multi-chain being a property chain doesn't encounter the same scalability issues. And I presume that it doesn't because of having a separation between capitalization and validation. But if that's the case, what are we sacrificing? Why can't we separate those two or something like that?
I mean, at the end of the day, you know, Ethereum is truly complete, so you could do it, but it's not designed for that, and so it would be quite a lot of fat. In the same way that you can do quite a lot of what you can do in Ethereum on Bitcoin. You know, if you create enough infrastructure and all the rest of it surrounding it, but it's so much fat food at the bottom. Well, this is the same. So it's just a different design choice taken at the beginning of the system. Now, how could we do things like consortium chains that have maybe much better scalability? The trick to it is in the validation function. So this is the function that collators run on their, validators run on blocks, on bits of data created by collators to check this out. Now, if they just do the standard thing, you know, I've been mentioning, where just execute all the transactions, you know, put them up with proof, then sure, we run into much the same. We can't really innovate that way. But we don't have to do that. The function is entirely arbitrary, as is the data that it operates. Yeah. So what we can do, for example, for consortium chains, you can say, right, well, actually, the consortium already has validators. It already has a means of checking that transactions are executed correctly. These guys are bonded, or there's some legal agreement between them. Yeah? So they can just go on and get on and make their blockchain. But what they want to do is ensure that their transactions can be moved and received, sent and received to all the other chains. What they want is the network effect, and that's carried out, rather than the commoditization portion. So they validate everything themselves, and they accept transactions coming in from the system, and they push transactions out to the system, and they accept the basic canonicalization. But what they do for validation, their validation function would be as simple as checking that the signatories of the consortium 10 of them, at least, let's say, 7 of them have signed the block. Now, checking those signatures is trivial, right? You do it in microseconds. Which means the consortium is free to employ supercomputers to actually process its own transactions and use whatever interesting, fully parallelized stuff it can, can imagine, it can invent. Now, the only thing that Polkadot cares about is that it's validatable using this function, which is arbitrary, which just checks the signatures, and that there's a queue of transactions going out, a queue of transactions going in, which they can. So that's how we kind of innovate.
So I presume multiple chains coordinating will be operating at the speed of the lowest common denominator.
So that's right. So the one important limitation with this design is the block times. Okay, so block times, at least until you employ cunning stuff in the validation function, block time is going to be the same, or at least there's going to be a lowest common denominator, which is the block time of the relay chain. So if the relay chain is, for example, 4-second blocks, you can't have a parachain that's going to be acting more or less normally with the 2-second blocks. You can have 8-second blocks and you stick around. And you can't go down, well, at least not easily. Now, the way that you can go down, if you're willing to set up the support infrastructure of having additional validators that are somehow incentivized to act properly, like a consortium chain, that would be quite reasonable thing to do. Then those guys can process blocks as fast as they want, because at the end of the day, all that's needed is signatures from them that they were processed correctly. And now, they then they rely on the canonicalization portion of the relay chain. So the relay chain prevents them from double spending, it prevents them from reversions or chain reorganizations or anything like that. But the validation, ensuring these transactions are valid and are executed faithfully, that's all done by these private guys in the consortium that just signed to say they did it. And that's all that the relay chain does. Now, the interesting thing is coming along when you say, right, well, actually, since these guys are just kind of signing for it, we just have to take their word, well, then we actually need the data to be in public, right? The data can all be encrypted, and it would still work exactly the same way, because these guys are just signing, so yeah, it's good. So we can imagine like internal private company intranet chains actually existing on Polkadot, and then being able to send transactions entirely seamlessly into Ethereum, and Ethereum sending transactions entirely seamlessly into these chains. So then you say, well, actually, one of these chains could be, for example, the Bank of England. The Bank of England is probably like a blockchain, and they've already been hiring people to actually design them. So what if Bank of England had a blockchain of Polkadot? It could be internal, it could all be encrypted. It would just be a means of Polkadot just provide a means of canonicalization and sending and receiving transactions, making it interoperable with all of the other chains. And that's entirely.
Just keeping an eye on time, maybe you can take this discussion about the networking afterwards.
Okay. Cool. Very good. So, if you've got any more questions?